Hello everyone. In this video, I want to introduce two basic sampling methods to you. They are the inversion sampling and the rejection sampling. Before this course, I want to again remind everyone that please like this video if you think it's useful to you, and subscribe to this channel to learn the latest data science courses. Last time we talked about data simulation. I told you that when a random variable's probability distribution is hard to calculate, we can draw a sample from this distribution and then use the sample mean and standard deviation to estimate the mean and the standard deviation of the random variable. So when we perform data simulation, the main problem comes down to how to draw a sample. We have several options. First, let's talk about the inversion sampling method. This method is very intuitive. Basically, we want to draw a random number that is between 0 and 1. And then we want to bring this number back to the distribution to find out which data sample corresponds to this random number. This method is intuitive, but it faces several limitations. First, the probability distribution sometimes is impossible to derive. It's very hard to get. Second, this method will not work with multivariate distributions, which means if you have two or more random variables, this method will not work. So in practice, we usually don't use inversion sampling method. But I want to focus on the second method, which is called rejection sampling. Let's talk about this method. Suppose we are given a distribution fx. We don't directly draw samples from fx. Instead, we want to find an easier probability distribution. Let's call this easier distribution gx. We want to multiply gx by a constant m. We want to make sure that for every data point, m times gx is greater than fx. We call m times gx envelope distribution because it covers the entire area of fx. Next, we want to calculate a ratio between fx and m times gx. We use uppercase R to represent this ratio. The last step is to draw a random number u. The range of u is between 0 and 1. Any number that is between 0 and 1. We want to compare the ratio R to u. If R is greater than u, we say the data point is from the distribution fx. It will be taken as a sample. If R is less than or equal to u, we say that data point is not from the distribution fx, then that data point will not be taken as a sample. This is a very complex algorithm. I think it's better for me to use an example to show you how this method works. Let's see the example. Suppose we have a random variable x. The domain of x is between 0 and 5. We are also given the distribution of x. It's fx on this slide. I want to use the rejection sampling method to draw 1,000 samples that follows fx. This is what I'm going to do. First, I want to calculate the possible values of fx because I need to identify an envelope distribution. And the envelope distribution should be greater than every value of fx. That's why I need to identify the minimum value and the maximum value of fx first. It's very easy to identify, right? Basically, you bring x into fx. And then we find out fx is between 0.075 and 0.325. The maximum value of fx is 0.325. In other words, we must find an envelope distribution that is always greater than 0.325. Next, I want to choose a distribution that is easier to calculate as Gx. In this case, I choose uniform distribution. Why uniform? Uniform is probably the easiest distribution. It's not necessarily to choose uniform, but it's the easiest. If you feel comfortable, you think other distribution is easier, you can choose other distribution. For example, if you are comfortable with normal distribution, you can choose normal distribution as Gx. There's no particular requirement. I just feel that uniform is the easiest, so I choose it as Gx. On the domain of 0 and 5, the height of a uniform distribution Gx is 0.2. Why 0.2? I use phi, which is the length of the domain, to divide 100%. I get 0.2. So the height of Gx is 0.2 on the domain of 0 and 5. But 0.2 is not always greater than fx, right? Because the maximum value of fx is 0.325. So what I do? I multiply Gx by 2. Then the height of Gx on the domain between 0 and 5 is 0.4. It can cover every possible point of fx. Then 2 multiplied Gx can be used as an envelope distribution. If this is not hard enough, here comes the most challenging step of the rejection sampling method. We need to calculate a ratio, the ratio between fx and m times Gx. I will use uppercase R to denote this ratio. According to the feedback I got, many people got stuck at this step. They didn't understand why we need to calculate R. Here is the reason. In the domain between 0 and 5, I want to randomly choose 2 data points, Z1 and Z2, as you can see on this slide. Let's talk about Z1 first. From Z1, we can draw 2 vertical lines, the blue vertical line and the red vertical line. I use the blue color to indicate the blue line follows distribution fx. I use the red color to indicate the red vertical line follows the envelope distribution m times Gx. As you can see, at the point Z1, the blue vertical line is very small. It's almost close to nothing, right? So at the point Z1, if you use the red vertical line to divide the blue vertical line, the value of R, of the ratio R, should be very small. How small? Close to 0. Now let's move to point Z2. From Z2, we can also draw 2 vertical lines, right? And at Z2, the blue vertical line is much higher. It is almost as high as the red vertical line. So at Z2, if you use the red vertical line to divide the blue vertical line, the value of R should be much higher. How high? Close to 1, because the 2 vertical lines at Z2 are almost at the same height. This example showed everyone a very important information. That is, the value of R can only change between 0 and 1. It can never exceed 1 because the envelope distribution is always higher than the real distribution fx. Next, we want to draw a random number u that ranges from 0 to 1, and compare u to the ratio r. If u is greater than r, what does this mean? It means u will create a blue vertical line that is greater than it should be. The point that creates U doesn't follow fx. It follows other distribution. We don't know what other distribution this data point follows. But anyway, it doesn't follow fx. The data value should not be taken as a sample that follows the distribution fx. But if U is less than R, the blue vertical line created by U is within the scope of the distribution fx. The data value that corresponds to that U should be taken as a sample from fx. This is how we use the rejection method to choose samples from a distribution. In the description section of this video, I listed the R code that can implement the rejection sampling method. I will not repeat the R code here, but I want to briefly talk about the limitations of the rejection sampling method. First, it can be difficult to identify the envelope distribution. Second, this method doesn't work with multivariate distributions either. Neither inverse sampling nor rejection sampling work with multivariate distributions. So if we have to deal with multivariate distributions, what should we do? We have other options, such as the Markov chain Monte Carlo simulation. I will talk about the Markov chain Monte Carlo simulation in the next video.